Now that's what we call long-lasting. Even though the two Voyager probes have been traveling through space for 47 years, their groundbreaking research mission is still in full swing. As is well known, the identical sister probes have now even passed the boundaries of the solar system and recorded a series of mysterious discoveries that leave even the most experienced astronomers open-mouthed. But what undreamed-of structures really lie dormant in the depths of interstellar space? And what about the extreme magnetic wall that one of the two probes detected here? Well, these questions are probably just as exciting as the incident that occurred in October 2022. That was when Voyager 1, which had already been traveling in space for 45 years, was hit by the most powerful gamma-ray burst ever recorded. Arfinhom. The same breath, however, the primal force of the spectacle also embodied a cosmic mystery. The outbreak and its afterglow simply did not fit our current models, and the experts were consequently confronted with an impossible event. From today's perspective, it seems almost comical when Voyager 1 and 2 plunged into the vast expanse of space on August 20th and September 5th, 1977. Nobody suspected that this was the starting signal for one of the greatest success stories in space travel. No wonder, after all, the originally predicted mission duration was just 5 years, and the probes were actually only supposed to collect new data about the outer planets of the solar system and their moons, which had so far remained largely unexplored. But after the spacecraft had taken the first, and in some cases, unique images of Jupiter, Saturn, Uranus, and Neptune, NASA decided to extend the mission and let the Voyager probes fly to the edge of the heliosphere. No sooner said than done, with a few decades of waiting. While Voyager 1 reached the Sun's protective magnetic bubble in 2012, its sister followed 6 years later. Never before had a man-made object penetrated so far into space, and in numbers. This means that the spacecraft have now put an incredible distance of 24.8 and 20.7 billion kilometers between themselves and the Sun. Conversely, the probes also gave Earth-based scientists a unique opportunity to study the extreme edge regions of our home system at close range and directly explore how our Sun interacts with the particles and magnetic fields outside the heliosphere. However, since Voyager 1 had already reached this uncharted world 6 years before Voyager 2, experts were all the more eagerly awaiting the arrival of the second twin probe to compare the previously collected data with the new information. And indeed, the comparison immediately revealed a surprising similarity. While the experts had previously assumed that the heliosphere was asymmetrical and had a shape that extended far back, the data from the Voyager probes suggests that we are dealing with a symmetrical, or, in other words, round structure. But the differences in plasma that were registered were all the greater. Before entering the heliopause, in other words, the outermost boundary of the heliosphere, Voyager 1 had detected a strong decay of the plasma currents, while the passage into the interstellar medium was characterized by strong turbulence in the surrounding plasma. Based on this, the researchers suspected a thick but unstable boundary region. But the case of Voyager 2 was quite different. On the one hand, it took just half a day to cross the heliopause, and on the other hand, it was not confronted with the extreme plasma tides that its sister probe had encountered. In other words, the heliopause presented itself as stable and thin this time. But what is it actually made of? Well, the experts point to the influence of the Sun. Since Voyager 1 encountered the heliopause during a minimum in the solar activity cycle, it can be assumed that interstellar magnetic fields and cosmic radiation penetrated deeper into the boundary region of the heliosphere. At that time, the strong phase of activity that accompanied Voyager 2's passage, on the other hand, may have stabilized the heliopause in combination with the strong solar wind, creating a huge magnetic wall. However, this was not the only thing Voyager 2 was supposed to discover in the outskirts of our home system. The probe detected something that had already been predicted on paper, sparking boundless enthusiasm among researchers. Apparently, there is indeed an extensive magnetic wall on our side of the heliopause, acting as an additional protective shield against cosmic radiation. In detail, the magnetic field in this cosmic barrier was stronger than any other magnetic field measured in the heliosphere to date and appeared to be extremely dynamic in nature. Experts say the solar magnetic wall is created by magnetic currents, moving toward the heliopause, where they subside and flow sideways. When the magnetic field direction of our host star reverses in the next activity cycle, this process starts all over again, but this time with opposite polarity. So far, so insightful, and yet we must not forget that we are still a long way from decoding the mysterious expanses of the heliopause and interstellar space. While the Voyager data suggests that the outer region of the solar system and the interstellar medium form a complex system, we are still only observing 2 points in this colossal system. In view of this, experts insist that follow-up missions are essential for a more revealing overall picture. However, such missions are still far in the future. Looking back, the technology with which the Voyager probes achieved their breathtaking milestones becomes even more astonishing. This technology, now from the state of the 1970s, can confidently be described as dusty. If you have a modern smartphone, you have a device with a memory capacity 1,000,000 times greater than that of the Voyager probes. Furthermore, the transmission data of modern mobile phone connections is almost 40,000 times higher than that of the 2 old probes. However, even the most robust technology from days gone by eventually reaches its limits, as recent developments demonstrate. While sudden contact interruptions are now almost a daily routine for the Voyagers, NASA has been pursuing a strict power-saving plan for several years to extend the probe's lifetimes. In detail, more and more components that are not essential for the spacecraft's operation are gradually being switched off. For Voyager 2, this most recently affected the plasma sensor. Conveniently, Voyager 1's required measuring instruments were still active in October 2022, allowing it to report a primal spectacle that caused a proverbial earthquake in the ranks of astronomers, the most powerful gamma-ray burst ever recorded. While speeding through interstellar space, Voyager 1's instruments sounded the alarm, reporting an inexplicably large influx of high-energy radiation. Acting as a harbinger of an unimagined spectacle, the probe detected an event that hit Earth 19 hours later. In detail, the recorded gamma radiation was so intense that almost all observatories, including NASA's Swift and Fermi telescopes, were instantly oversaturated. It soon became clear this was the effects of an unprecedented gamma-ray burst, later dubbed the brightest of all time, BOAT, and scientifically named GRB 2021-A. The record-breaking event immediately raised a fundamental question: what triggered the extreme eruption? With an energy of 18 tera-electron volts and brightness 70 times greater than any previously observed eruption, the spectacle pushed scientific boundaries. Beyond its intensity, the eruption also produced a strange jet of radiation that challenged current models of such events' afterglows. Astronomers uncovered a new component in the radio range of the jet that left them baffled, while other ranges of radiation exhibited strange anomalies. The jet appeared unusually strong and focused. April 2024, astronomers finally identified the origin of this record-breaking outburst. However, the finding only raised more questions. The intense radiation, which even altered Earth's ionosphere, originated not from a colossal mega-explosion, but from a seemingly normal supernova. Follow-up studies with the James Webb Telescope's high-resolution near-infrared spectrometer revealed this surprising result. How could an ordinary stellar death trigger an event that occurs on Earth only once in 10,000 years? This question remains unanswered. Astronomers suspect that extreme Gamma rays could be linked to a special form of explosion. When rapidly rotating massive stars collapse, they generate particle jets racing through space at near light speed. If these jets are particularly narrow and concentrated, they create a bright, high-energy beam. The record outbreak's Jet 1, of the narrowest ever recorded, suggests the supernova's energy might have been similarly concentrated. While the mystery of such jets remains less understood, their implications are groundbreaking.